In this video, we'll do several examples of logarithmic equations. Before we get started on solving, for our first example, we're going to solve the equation 4 times the natural log of x equals 36. And we want to make sure that we give exact values. So while we can use our calculator to find an approximation, we're just going to leave our answers in the exact form. So for our first example, I'm going to start by dividing by 4. That's going to give me the natural log of x equals 9. To solve this equation, all we have to do is convert. So recall that when we have log base a of x equaling y, that's equivalent to a to the y equals x. Well, that's what we have here. The base happens to be e. So if we convert this to its exponential form, it will give us e to the 9th equals x. And we've solved. For this next example, it's already in this log form. We're just going to convert it to exponential. 3 to the 1st equals x cubed minus 5. Adding 5, we get x cubed is 8, and we get x equals 2. For our third example, we have a log plus a log equal to another log. Well, if we go back to our properties of logarithms, I should be able to condense these logarithms as the log of 2x plus 1 times x equaling the log of x plus 8. Now what we know is that if the log of one number equals the log of another number, then those two numbers must be equal. So now that I have a log equal to a single log, I can say that this expression is equal to this expression. So we'll have 2x squared plus x equals x plus 8, or 2x squared equals 8, because the x's would subtract and go away. So now we have, if dividing by 2, x squared equals 4, or x equals plus or minus 4. Now, this is a good opportunity to refresh your memory on the domain of a logarithm. The domain of the expression y equals log base a of x is only 0 to infinity. You may recall that the graph of a basic logarithmic function has this vertical asymptote, and of course we can shift that around. But what we know is that the argument of a logarithm, this piece right here, has to be between, well, it has to be positive, and it cannot equal 0. So anytime we get a solution, it's always necessary to check that the proposed solution results in logarithms of positive numbers only. So let's go back to our first one. Notice that e to the 9th is a positive number. Keep in mind that's not what I'm looking for. I want to make sure that when I plug this in, e to the 9th, that I'm actually that I'm not trying to take the log of a negative number. This is a positive number, so we're okay. Similarly here, if I put 2 in, I'll have log base 3 of 8 minus 5. That's 3, and we can take the log of 3 because it's a positive number. For our last example here, though, if I tried to plug in 4, log of 8 plus 1 plus the log of 4 equals the log of 4 plus 8. All of these will be positive and we'll be fine. And notice I'm checking it in the original because that's what I want to make sure that the domains are okay there. And then when I plug in the negative 4, I get the log of negative 8 plus 1. And you can see right away that that's the log of a negative number. So our only solution here is x equals positive 4. These, the ones I boxed here, these are just our proposed solutions. And we need to make sure that when we plug our proposed solutions back into the equation that we're not asked to take the log of a negative. And that's super important because I didn't get rid of the negative 4 in this situation because it's a negative. I got rid of it because when I plug it in, I'm asked to take the log of a negative. So let's look at another example. Here we have the log base 3 of 4x plus 1 times x plus 1 is equal to 3. Here I can just convert this logarithmic equation into its equivalent exponential equation and get 3 cubed equals 4x squared plus 5x plus 1. And 3 cubed is 27. So if I subtract 27, I get negative 26. Now I want to solve this. 4 times negative 26 is going to give me negative 104. And I'm looking for numbers that multiply to negative 104 that add to 5. So here I've made a list of factors of 104, and I want it to be negative, and I can see that if I add positive 8 and negative 13, I will get that negative 104. So this does factor. Quick refresher, if you divide these two numbers by the lead coefficient, which in this case is 4, and reduce, you're going to get the two factors, x plus 2 and 4x minus 13. So our solutions here are x equals negative 2 and 4x equals 13, or x equals 13 quarters. We're not quite done. We do have to check our solutions. And so let's check. Does 4 times negative 2 plus 1 times negative 2 plus 1, is this a positive value? So we have negative 8 plus 1, or negative 7 times negative 1, that's positive. So we're good with the negative 2. And then if I plug in 13 quarters, 4 times 13 quarters plus 1 times 13 quarters plus 1, we'll get 14 times 17 quarters, which is positive. So in this case, both of our answers are legitimate. Okay, one last example here. In this case, we have a log plus another log equals 3. Log base 2 of 2x minus 5 times the log base 2 of x minus 3. We know that when we have a sum of logs, we can multiply these together. Log of the product equaling 3, and we have log base 2. So this is log base 2 of 2x squared minus 11x plus 15 equals 3. So since I have a logarithm equal to a number, I can convert it to its exponential form. 2 cubed equals 2x squared minus 11x plus 15. 2 cubed is 8, so subtracting 8, 2x cubed minus 11x plus 7. And we try to factor this one. 2 times 7 is 14, which is 1 times 14, or 2 times 7. And we can't get 11 out of that. So our option now is to use the quadratic formula. So using our quadratic formula, we'll get approximately 4.77 and 0.734. Take a moment and verify that. And then let's ask ourselves, if I plug the 0.477 in, I should get something here around 8, maybe 10 minus 5, but definitely positive. 4.77 minus 3 is also positive. So this answer checks. 0.734, on the other hand, would, when I subtract 3, that's definitely a problem. So in this particular case, I only get x equals 4.77. There are 2 additional examples in your notes. The first one is the following: the natural log of e to the natural log of x minus the natural log of the quantity x minus 4 equals the natural log of 5. So I notice right away that I've got this exponent. I'm going to bring that down in front. That's going to give me the natural log of x times the natural log of e minus the natural log of x minus 4 equals the natural log of 5. And we happen to know that the natural log of e is just 1, so we really have the natural log of x minus the natural log of x minus 4 equals the natural log of 5. Now, it's a real common mistake here to try to divide through by the natural log, but as we know, ln without any kind of an argument doesn't mean anything. We can't separate it from its argument. So we're going to use our properties of log. Since I have a minus here, this is going to be the natural log of x divided by x minus 4, which is equal to the natural log of 5. And then we use our property that says if the log of one number equals the log of another number, then those numbers have to be equal. So now we just have a linear equation, x equals 5x minus 20, or negative 4x equals negative 20, or x equals 5. If I plug 5 into my original here, 5 minus 4 is 1. That should work. The natural log of 5 is positive also. So our solution is x equals 5, and it does check. The last example is the following, and it's a little more difficult. Log base 2 of 2x minus 5 plus the log base 4 of x minus 3 equals 3. So up until this point, when we were dealing with our log equations, if we had logs, they were always the same base. And in this case, they are not. So what we're going to do here, we can change the base we know to anything. But since we know that we can use our calculator with base 10, I'm going to change this to base 10. So this is going to be the log of 2x minus 5 divided by the log of 2 plus the log of x minus 3 over the log of 4 equaling 3. And I notice that 4 is really 2 squared. So I'm going to rewrite this as the log of 2x minus 5 over log 2 plus the log of x minus 3 over 2 log 2 equals 3. So I'm just using that exponent rule and bringing that down. So now, if I multiply both sides by 2 log 2, my fractions will go away. So I'm going to multiply everything by 2 log of 2 2 log of 2 on this side. So on this side, we're going to have of 2x minus 5 times 2 plus the log of x minus 3, because everything will cancel here. And then on the other side, I'm going to have 6 log 2. And then I'm going to simplify. So if I put this back together so that I have a single logarithm, and I bring this 6 up, I'm going to have the log of 2x minus 5 squared times x minus 3 equals the log of 2 to the 6th. So we can now set this expression equal to this expression, and it's going to start to get messy. So let's take a look. So if I multiply out the 2x minus 5 squared times x minus 3 equaling 2 to the 6th, you will get, and I encourage you to multiply it out and check it, but you will get 4x cubed minus 32x squared plus 85x minus 75 equals 64, or 4x cubed minus 32x squared plus 85x minus 139 equals 0. Now what I would probably do at this point is I would plot my function. I would put it into y1 in my graphing calculator, and I would look for where it crosses 0. So let's take a look. So I can tell that my graph is crossing approximately 5, and if I use my calculator, I get x equals 5.198. Now we should check and make sure that's going to work. And if we look back up in the original here, if x is about 5, 5 minus 3 is going to be 2 or positive. 10 minus 5 is going to be about 5, so we're in good shape. That concludes this video on logarithmic equations.